Yo, yo, yo! So today what we're going to do is we're going to look at some advanced logic. It's logic part 3. If you haven't seen logic part 1 and 2 and you really don't know what you're doing with logic gates in Minecraft, you probably want to check those out and explain some of the more simple steps to this in case you get a little bit lost. So today what we're going to do is show you how to build a little bit more of a complicated circuit. So this one is a 2-bit arithmetic logic unit with 2 different operations. So this isn't a full arithmetic logic unit. If you don't know what that is, it's basically the maths engine behind a computer. All a computer does is just shoves lots of numbers around some memory and then does different things to those numbers. By numbers, I mean binary numbers, so it's just lots of ones and zeros. What this one does is it takes two 2-bit numbers, so that's 1 and a 0, a 0 and a 1, 2 zeros, 2 ones. It takes 2 of those and it either ANDs them together, either bitwise AND them together or bitwise OR them together. Now, you don't really need to know what that is exactly, but you will need to know, if you're going to build a big arithmetic logic unit, you're going to actually build a computer, what you want to do with it, or what operations you want to do. But just as an example of how this thing's actually possible, I'm going to show you how to build one. So the 2 operations I want to do, bitwise AND, bitwise OR, what that means is we take each bit of each number, so the first bit of one number, the first bit of another number, and then we AND them together, or we can do bitwise OR, which is just the same, except we use OR. So over here, we've done a karnaugh map in nice Minecraft style. If you're colorblind, I'm sorry, I couldn't think of an easier way to do this, but I'll show you which one's which. Karnaugh map, spelled like this, Karnaugh map. You might want to look that up somewhere else if you're a little bit confused what's going on, but basically what it does is it helps us simplify the circuit, the logic circuit, by describing for which inputs, so these ones on the outside, these represent the inputs, red for off, green for on, and then this thing here shows us what the output should be, and the output is just 1 bit. And why that might be a bit confusing is this one is just any bit, because of the fact that with a bitwise AND or bitwise OR, it doesn't actually matter which one you're doing it to, you're just doing the same thing to both bits of each number. So it doesn't. You can do the same thing, exactly the same thing with this with a 1000-bit number. If you're doing a bitwise AND, bitwise OR, it doesn't actually depend on the other ones. So you just do the same thing. So and if this is a little bit confusing, you might want to look up how karnaugh maps work so you get this a little bit better. But basically, when A and B, whichever bit you're looking at, is off, and this extra little thing, A and B being the 2 different numbers we're looking at, this extra little thing, which is a control value, which when it's off does one thing, when it's on it does another thing. Over here, I can't actually remember which one's which, so I'm going to just go over here and check out what's going on. This is the control one here. Okay. Okay, so that's an OR. So when this thing is off, we've got an OR going on, and when this thing is on, we've got an AND going on. So, oh my god, computer's gone crazy. So this rail here is the OR, and this is the AND. Okay, so when control's on, this is the AND lot, and when this is off, it's the OR lot. So that determines what's going to happen. So for both off, nothing happens and nothing happens. For A off, B on, we want on for this one and off for this one. So this is the OR condition, this is the AND condition. So if we AND those 2 together, we get nothing. If we OR those, we get this one. And when they're both on, AND and OR should both give us, depending, it doesn't really matter which one it is, we're both going to give us an on. And for A on, B off, we should get on for the OR condition, but an off for the AND condition. So the green ones represent the conditions where we want the output of each bit to be on, and the red ones represent the output of off for those particular conditions, which are these things around the outside. So how we actually use this to make the circuit simpler is we group these green ones together. So the best thing to do is to group them in the largest groups possible of rectangles or lines. So we're going to take a rectangle around this thing. Oh, the computer's going crazy again. We'll take a rectangle around these 3 at the top. Okay. That might become clear later on. Again, looking at Karnaugh maps in a book is probably more sensible, or just go on the Wikipedia page. But what we need here is for these three here is the equivalent of saying A or B. And if we look here, if we have A or B on, if we just look at this top row, A or B on, then these three are on. Okay, so that's basically the same as just an OR gate. You know, A or B, doesn't matter which, or AND, that's fine. So one or the other, or both, we get an on. And then when they're both off, gives a not, gives a nothing, gives a 0, an off. So this is basically an OR gate at the top. So A or B, but this is only really the case for the control being off. Okay, so the control off and A or B. So that's our first thing. Now, if we look down here, it actually shows us in Boolean logic. Again, looking it up in Wikipedia is probably a good time to do that right now. So A, and then the plus means or in Boolean logic, A or B, and then we AND that with not C. This little dash means a not C. So that means when C is off, okay? So when C is off and A or B, that'll give us an output of on. So provided we know this, when C is off, A or B will give us, the result of A or B will give us an on, which obviously means when everything's off, we'll get nothing. But we also have this lot. So when control is on, we've got this one over here. So like I said, making the biggest rectangle possible. So we're going to group these two together, which is when A and B, and you see as you kind of draw down there, you know, A and B gives us this line here. So we can actually ignore what's going on over here because it doesn't actually matter which one it is. A and B there and A and B there, doesn't matter whether the control's on or off. So when A and B is, when A and B is on, okay, when it's positive, on, one, whatever you want to call it, when it's green in this case, then the output is going to be on. So we've got two different conditions for the output to be on, high, one, redstone, lit up, whatever you can call it, is when A or B and we've got a not C, and C is off, or we've got just the result of A and B. Now it doesn't matter that these overlap, in fact that's pretty sensible. So it doesn't matter that these things overlap at all. So we've got, here's the result, the output is A or B as long as there's a not C, so not C and A or B, or just A and B. So how we actually do that is we just literally make that out of logic gates. We put A and B through an OR gate, and then we AND that, that's what the dot means, we AND that with a not C, so an inverted C, and then we OR the output of all of that with the output of A and B. So we have a look at how that actually looks. If we look at just this one, it's the first bit of A, and that's the first bit of B, and that's the control. So A goes through an OR gate, you see it just goes under that bridge there, so that's the OR gate. So that's A or B. There's an AND gate, and that AND gate is actually C there, that's the control. So that's A or B and C, and not C, sorry. You can see it actually goes through an inverter there, because we only ever use not C. So not C goes through there. We've got A or B ANDed, that's that thing there, with a not C. So we've got the first chunk of that condition, that expression, which is here. So we've got A or B and not C. And then we put that through an OR gate with the output of A and B. So that's the A and B, just over there, different part of the playground, but basically the same thing. So A and B, that's through AND gate, and then gets ORed with the output of A or B and not C. So that's the A or B and not C chunk, and then it goes wee all the way around here and gets ORed with A and B, that's the AND gate there. So it looks a little bit complicated, but if you just follow it through, make sure you use plenty of repeaters and all that jazz, just to make sure everything reaches where it wants to go. But basically that's how you make it. So you only really need a couple of logic circuits. If you didn't do it the way we looked, we'd actually need one set of logic circuits for every single one of this. So we'd actually need 8 sets of logic circuits. And here we only need 1, 2, 3, 4. So we've actually half the number of logic gates needed. And we might even need more if we're going to go for something really complicated. So this is actually a really efficient way of making some really complicated logic circuits. So if you wanted to, add more, add more different functions, controls, whatever. So instead of just bitwise and bitwise or, you could add the two numbers together. You could take one away from the other. You could make one negative. You could flip all the ones and